I am Anil Kumar, sharing with you some information about number systems and how do we represent these numbers on number line. Let me begin by thanking the great scientists of our past, and I'd like you to research a bit, Google Aryabhatta to know something about our numbers. Fortunately, we don't have to depend on sponsored scientists these days. We can Google and get the facts. I'll also talk about classification of numbers, basic set notation, and number line. This video will concentrate on topics which really matter, but I should and I will touch upon the basics of number system where we have spent hours in just knowing what different number systems are. Let me list them. We call one set which is called natural numbers, right? Then we evolved into integers. While in between, we introduced whole numbers, but many times that is skipped. Okay. So we actually moved from natural numbers to integers, introducing whole numbers which included 0. And then we moved on to rational numbers. And then we talked about irrational numbers. And moved on to real numbers. Well, we'll end here. We'll not go to imaginary or any other numbers. We are limiting ourselves to representing numbers on number line. So the idea here is to just restrict ourselves to represent numbers on number line. So that is the key for this particular video. So that's the domain in which we are working. Now this video can be used by college students also as an introduction to algebra. Okay, so let me say something about Aryabhatta here. You should Google and find the facts. Well, when we talk about this great person, we are referring to something called 400 BC, right? And a person who was 23 years old. And this person at that age had an idea about numbers which we call irrational. For him, pi, which we now understand, made sense. And he gave a value which was correct to 4 decimal places. Now these are important facts to share with you, since when we talk about number systems, what do we say for half an hour? We say we start with the natural numbers, which are numbers like 1, 2, 3, 4, and so on. And then we felt the need of 0 and negative numbers, and so we introduced whole numbers. Let me write down whole numbers here. 0, 1, 2, 3, and so on. So including 0 means whole numbers. And then we felt the need for negative numbers, and so we introduced -1, -2. Called them set of integers, and then we found that we definitely need some other numbers which are ratios, kind of fractions, and so we came up with numbers of the form of p over q, where q is not equal to 0. And then we discovered that there are some numbers who cannot be written in p over q, so we call them irrational numbers. And here we gave 2 characteristics. One was non-terminating, so that is to say that if you have a number which is something like, well, on a calculator, if you say square root of 2, for example, then you get some number which is non-terminating, right? So, and non-repeating. right? So those kinds of numbers could not be represented as P over Q. Non-repeating, if you calculate the value of 1.3, what you get this as 0 point, then 10333, right? So it kind of repeats, correct? So these are So these are the numbers which were kind of difficult to understand, and we call them irrational numbers. Now, to include these irrational numbers into our number system, we introduced real numbers, right? So that is how we got to real numbers. So we didn't do much about irrational, so we kind of skipped it. And we introduced symbols for each numbers. We write natural numbers as this kind of n. Double line, I don't know why. So integers, we write double line again. Rational numbers are, I'll use single R, but double line again. I'm sorry, this was for real numbers. Okay. And for rational numbers, we use the letter Q. Okay. So these are the symbols for our numbers. So we kind of missed the symbol for irrational numbers. I couldn't find any. But the closest we can go to is, let me write it here, irrational. It is really irrational. We say it is R minus Q. That makes sense. So something which is not real, something which is real but not rational. Okay. So we have R minus Q as irrational numbers. And what people discover now is that we have more irrational numbers than rational numbers. All our scientists are given a lot of credit for expanding the number systems to include everything, which helps us to explain what is going around the world, as we can actually model everything and represent in this language of mathematics, right? So that brings us to now the set theory. I think we're done with the numbers and you know about all this. So we'll kind of move to the language of mathematics, which helps to explain many things which we haven't understood so far. Now let's talk about set notation to represent numbers. Well, I'd like you to go through set theory and understand what it is all about. But here I'll give you few things in which are necessary for us to know, right? So first thing is, what is a set, right? We say set is a well-defined collection of objects. So that is basic definition, well-defined collection of objects. And how do we represent a set? Well, when we say collection of objects, in that case, the objects could be finite objects or they could be infinite, right? So second, we are not limiting to mathematics. Let's say mathematical terms. It could be any objects, right? So it is a very general theory which could represent many things. But in our discussion, we'll concentrate more on the number systems, right? So I hope that is clear. Now, how to represent our numbers? So for a set, we normally use brackets, this kind of brackets, right? So braces are used. Let's say we call them braces. So one to begin, right? So you can say begin or start. And the other one to end. So another to end. In between, we have objects. So when we say well-defined collection of objects, then these objects we also call rather represent them as, let me use different ink, elements, right? Or sometimes say members. Now, a set will also have a name, right? So we normally, it's preferred to write a name here so that we can communicate better. So I think these are the basics which you should know. Now, when we say well-defined, let me highlight that also. How do we define it? Okay, well-defined. So when we say well-defined, let's say define. Now, how do we define it? One way is you can just list, right? So no need to write description. Other way is to write a rule, something like this. So it could be a rule or a list. So to define, we use a language. Let me use another ink for language. Okay. So we are slowly getting into more details I didn't want to get into. Okay, language. So the language, we use few terms which are kind of, this is very common. It says belongs to. Okay, and then we have this symbol, a straight line, which is giving you a condition. So this is conditional, such that, or it gives condition. Okay, we'll put all the things together and then I hope they will make sense, right? So, and we also use these dots. So these dots, we'll call them ellipse. In general, in English you use ellipse, right? But they represent that it extends to infinity. Extends to. So sometimes it is kind of an extension to the rule, we can say, right? Extends, but based on the rule. It may or may not extend to infinity, but it could be sometimes missing terms in between, which are interpreted with the rule. So I think that is enough. Okay. Yeah, we are going to use only these symbols. Let's give some examples. Let's begin with the defined objects. So let's say we call a set P, and we'll say this set has numbers which are prime numbers. Let's say less than 10. So in curly brackets, I'm just putting a rule. It is good enough. It represents a set. So the same set you could list. All the prime numbers less than 10 could be 2, 3, 5, and 7. Do you see that? So you could describe or you could write like this. So that is a finite set. Perfect. Okay. So that is one way in which 2, 3, 5, 7 are elements of this set. Correct? We could have set of natural numbers which could be represented as 1, 2, 3, 4 and these ellipse. So that becomes infinite set. Do you see that? So this becomes infinite set. Now this goes forever. Well, you could have integers, and let me call that as set A, right? So it could be normally a capital letter. So we are saying A, and we call this as like in another variable, so n belongs to, right, set of integers. So for integers, we use the letter Z. So n belongs to set of integers so that n is between, we give two limits. Let's say minus 10 to plus 10. So that is another way of defining your set. Well, this is finite set. So we introduce all these terms and I hope you get good examples here. So that becomes a finite set, right? Finite set. We are restricting ourselves to known numbers. And here, yeah, this is also known, but we don't know what is the last number, correct? So that extends forever. Okay. So that is how you could represent the sets. One very important set here, which I should say, is a null set. Null set. We also call it a void. Void means nothing, represented by letter phi, or these braces with nothing inside. So that becomes a null set. Okay. Remember one thing, that if I set B is having one element, 0, it means it is not null. Okay. So be clear about it. So this B is not a null set. It has one element. So sometimes you have to figure out how many elements are there. So in P we have 1, 2, 3, 4 elements, okay? And in B we have one element, and in null set we don't have any element, no elements at all. Is it okay? So I think that is enough, and we'll now take a... Now let us understand a very important concept of representing real numbers on number line. That is actually a connection between geometry and algebra. Let me show you how. A straight line here, arrows at the two ends indicate that it extends on both the sides. So on this line, which is a set of points, I'm marking a point right in the center and labeling it as 0. Now what you see here is that on a line we have set of points. So that is geometry, right? So the line is geometry. Now marking numbers on it is algebra, right? So we are connecting numbers. All right. So that is also called one-dimensional representation. Coordinate plane is two-dimensional, correct? Okay. So what we do here is that on a number line, we mark a point and we say this is our origin. So this is a very important point. It has different names. Origin is most popular. Numbers on the right are positive and on the left are negative. As you move right, we are saying increasing. So numbers are increasing as you move right, and as you move left, they are decreasing. Right, so let us say in general, let's take two numbers, A and B. So if I take two numbers A and B, and this symbol here, as you now understand, is belongs to, we say set of real numbers, right? So R. So we have two numbers A and B, which belongs to set of real numbers. These numbers can be represented on the number line. Let me show you how. So let us mark arbitrarily some point and name that to be unit distance away from origin. So we have created our own scale. We are saying this much of distance moved from the origin O or 0 to the right will be one number represented by one unit. So if I have same markings, kind of a scale, I can label them as 2, 3, 4. Positive, as you go up, you can see all numbers to the right are bigger than the numbers on the left. If you move to the left side of origin, the numbers are decreasing by 1 as we keep a standard measurement mark. Do you see that? So that is how you can actually represent numbers. So what I've done in this process is I've represented some integers, right? Do you see some integers there? So likewise, we could represent any integer on a number line. Now let's take some fractions, okay, or rational numbers. So for example, the number here, right in the center, could represent minus half. So that becomes a rational number, right? Now, numbers to the right, we could have a rational number, let's say 1.5. I should write 3 over 2. So in the form of P over Q, where Q is not equal to 0. So that becomes the rational number. Let's take an irrational number. Okay, irrational number pi could be a good irrational number to take. Approximately 3.14, so it's very, very close to this point, right? So that is pi for us. So likewise, you have seen that we have actually shown different kinds of numbers, right? Square root of 2, right, could be represented 1.14 somewhere here, right, in between. So likewise, as you can see here, we can represent all the numbers, real numbers, on a number line, correct? Now, we'll talk more about, in general, two numbers like A and B. So what you notice here is that if A is greater than B, that means what? This means greater than. Okay, some of you may not know that. This symbol, let me write here. This symbol here indicates, when we write like this, we mean A is greater than B. That really means that A minus B will be a positive number. Is that clear? That means that A is on the right side of B on the number line. Okay, so that also means that A is to right of B. Does it make sense? So when we say greater than, it means like this. Now if I have to represent A less than B, for example, if I say A is less than B, that means A is on the left side. So this means A is on left side of B. Does make clear? When we say A equals to B, that means they are the same points. Is it okay? Well, let us explore this, take some examples. So what we will do now here is, we'll represent real numbers on a number line in a different way. For example, I have to write a number n, which is, let us say, greater than 2. How do I represent this on a number line? So on a number line, let's say, I'll make smaller things now. 2. So we can mark 0 and then the number 2. Since all the numbers are greater than 2, we'll make a hole here, or not filled in circle, and an arrow to the right. So that represents all the real numbers greater than 2 on a number line. Is that clear? If I have to show a number n which is less than, let's say, minus 3, let me take minus 1. On the same line, I'll draw that number. So if that is unit 2 for us, on this number line, 1 will be kind of half of this. So this is 1. And if I want to actually represent less than equal to, let me take less than equal to. In that case, the difference is we are including 1. So I'll fill this up. Is it okay? So I'll fill this up and then take all the numbers to the left side. As we saw, left side is decreasing. So less than minus 1. And this point here is at minus 1. Do you see that? So numbers less than or greater than equal to can be represented by a solid line with a head of an arrow as shown here, right? Now if I have to represent a number n which is between two numbers, let us say minus 3 and minus 5. How do I do that? That could be done like this. On a number line, let's mark our 0 and then take the two numbers, and let's say this represent, let's say 1, right? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. In that case, we are talking about numbers between minus 3 and, I'm sorry, this should be positive 5. Okay. So, yeah, minus 3 and positive 5. So, the numbers will be from minus 3, 1, 2, 3, a circle there at minus 3. And to the right, 1, 2, 3, 4, 5. Not including these, therefore these circles are not filled in. So that represents all the numbers, all the real numbers between minus 3 and plus 5. If I have to represent numbers which are greater than or equal to, let us say minus 2, but less than 3, how do we do that? Well, whenever we say equal to, that circle has to be filled in, right? So let us say this is the origin O, then the point, let's say this is minus 2 for us, and on the number line this is, let's say, 3 for us. So since it includes minus 2, the circle here will be filled in, and at 3 it will be open-ended, open circle, and everything in between is what is being represented by this inequality. So in a way, we have used inequality to represent numbers on a number line. Now, all these two examples, and which we have seen here, they can collapse into one unit. Do you see that? But we could have examples which are kind of different. For example, how do we represent that n is less than minus 2 or n is greater than 2? Now, to represent this on a number line, we'll have something like this. Let us say this is the origin, minus 2 being on the left side, plus 2 being on the right side. Now, what are we saying here? We want to represent all real numbers which are less than minus 2. That means open circle here, and that becomes less than. Less than means left, right. Greater than means right side of 2. Right side of 2 and like this. Do you see that? So what we see here is a gap in between. So whenever there is a gap in between, we write it as two different inequalities, combination with or. Do you see that? So these are different ways of representing numbers on a number line. Now this is very interesting. You could also represent numbers saying n is not equal to 5. If I say n is not equal to 5, what we are saying here is n belongs to real numbers for all our examples. How do we represent that on a number line? That really means that, let's take this as origin again. 5, let's say this is 5 for us. Now we are saying n is not equal to 5, but everything else. That means everything else, right? But not 5. Do you see this? So a hole at 5 or not filled in circle at 5 represents n not equal to 5. Do you get an idea, right? So that is how we represent numbers, the real numbers, on a number line. Correct? Now, based on all this, we can have a summary. In general, we'll talk about two numbers, a and b, which belongs to real numbers, and we'll have 9 conditions where we'll show you how we can represent set of numbers on a number line. All right, so let's begin with one set which does not include the endpoints. So if I have number, let's say from A to B, not including A and B, which is to say that we are saying that the number n is greater than A but is less than B. Do you see that? So that is how it is being treated. Now that notation can be represented on a number line by, so number line always assume that this is ends with arrow, okay? So that really means that somewhere there is a point A, somewhere there is a point B. From A to B, so A is a smaller number. Not including means a circle at A, circle at B, not filled in, and everything in between. So this is what is being represented by the ordered pair. This is also called kind of an ordered pair, right? So numbers have ordered, all real numbers. When we say numbers on the right are greater, that means there is an order, right? Okay. We could do something like this. A is not included, but B is included. That is to say, the number n is greater than A, but is less than equal to B. In that case, it will be represented like a filled-in hole for B, right? But an open circle at A. Does make sense. We could have the other way. That is to say, the numbers include A, but they do not include B. As an inequality, any number which is greater than equal to A, but less than B, could be represented on a number line by saying that this is included means filled in A, but open B. Not including B, correct? Or we could have a condition where both are included, right? So both are included. That means you understand it should be filled in for both, right? So these are four different ways in which you could do the numbers where they are bounded in a way at two ends, A and B. Both are included means filled in. Do you see that? Now, you could also have conditions where we say from A to infinity, and infinity can never be bounded. So we say that n is greater than A. Do you see this? N is greater than A. Normally, we'll write this as like this. N is greater than A. Correct? Let's use conditions where infinity is involved. So we have taken the first one here, that the number is greater than A, which I'm saying could be written as A is less than N, or better way is number N is greater than A. Let me represent this on a number line. Now when I say that the number is greater than A, that means it is on the right side of A, right? So, but not equal to. So it'll be like this. So that is A for us. Now we could have including A, right? So it becomes, but you can never include infinity. Remember, infinity is not a real number. Let me write down here. Infinity is not a real number. Now that could be a test question at times, right? So it's very important to understand this part. So in that case, we have a filled in circle at A, arrow pointing towards right. Now it could be the other way. That is to say, we could have from infinity to A, right? So in that case, all the numbers we are talking about are less than A, not including A. So on a number line, they will be represented like this. Now we could have similar example as we had earlier. So when I say A is greater than, let me write down inequality also here. We say N is greater than equal to A. Now in this case, n is less than A, right? Which is represented like this. So n and n could be between, I'm right, minus infinity to A, where A is included, right? So that becomes another condition. A is being included. So we have 8 conditions here. Now what could be the 9th condition? Can you tell me? The 9th condition is all real numbers between negative to positive infinity. Do you see that? So here we say that n belongs to real numbers, all real numbers, and if this is the line, the number line, then it is being represented, let's say 0 here, by all the points on this line. Do you see that? So this page gives you a good summary of how we could represent all the real numbers on a number line. So I hope that makes sense. Let's move on and take some more questions. Now this could be test questions for you as a review. We have done a lot of examples. I would like you to fill in a table here. So let us say I have to represent a number n which is less than A. How do I write in the notation which is like in brackets? And how do I represent this on a number line? So this is the exercise which is for you to do. Let me do the first case. We are saying all the numbers are less than A. That means they're on the left side. So on a number line, we'll mark A. We don't know whether it is on the right of origin or the left of origin. So we avoid writing the origin O. Is that okay? But we know it is towards left of A. That means less than means we are approaching minus infinity. So it's from minus infinity to A. You get an idea, right? So that is how you're going to do it. So this was your question number 1. Okay. Now let me write down 2 or 3 questions here for you. So we want you to write numbers which are between A and between B, where both are included. Now let me give you a point here when we want n to be less than equal to 10, but should be greater than minus 5. I want you to represent n not equal to minus 2 on a number line, and I want to represent n equals to 5 or let's say plus minus 5 on a number line. Okay, so I want you to take some time and represent these numbers on a number line. Also write in this notation, right? So that is the question for you. You can pause the video, answer this question, right? I'm taking time here so that by the time I finish with these lines, you have your answers, right? Okay, so this one should be all the numbers between A and B, so both are included, right? So you have to put square brackets whenever equal to sign is there along with inequality. Now in this case, it's a open bracket and this one is a closed bracket. Is it okay? And the numbers here are minus 5 and 10. So I'm using different ways of filling them up, right? Now, such numbers n not equal to minus 2 cannot be placed like this. Do you have sense? Right? So that's kind of very difficult. So what you could do here is that you could use a notation which is, it's kind of tricky. Let me just mark here and then I'll show you how to write this. So what you can do here is that I'll get to this end. Let's go to this place. Okay, so from A to B both included, just fill this up. This is fast, right? So let me catch up with you. Not including minus 5 but including 10. Okay, in this case you can of course show where origin is. Not including minus 5, you should show where origin is. not including minus 2. So this is minus 2. We make a circle here and kind of like this, correct? And n is equals to plus minus 5. So let's say this is origin and this is minus 5. So it is equal to, so we'll fill this up and we'll fill this up. So that becomes plus 5. Okay, getting back to this. That means, as you can see here, from minus infinity to minus 2 and then from minus 2 to infinity. So it's kind of combination of like this, minus infinity to minus 2 not including, or sometimes we write union, u, and then from minus 2 to infinity. Do you see that? So that is how you could write these numbers. Okay. Now sometimes we use another notation where we could also write this in set form. So we say n belongs to real numbers, so that n is equal to, we could just list this. Okay, so that was not good. Plus minus 5. But better way to do this is just to list plus 5 and minus 5. Do you see that? So this is a better option. Else, you can use three groups like this to represent these numbers. From minus infinity to minus 5, or minus 5 to plus 5, or plus 5 to infinity. So what you also see almost at the end of this video, that there are different ways to represent numbers. We could represent them on a number line. We could represent them with inequality and with bracket notation. So these are different notations also in the set form, right? So what we learned here is that we could use number line. How do we represent numbers? So we could have set, we could have number line, we could do inequality or interval notation. We also say bracket notation. So I hope that makes sense. Feel free to write your comment, share your views, and if you like and subscribe my videos, that'd be great. We'll actually take up absolute functions and how to represent some of these things using absolute functions as absolute values on a number line. We'll take that up in the next video. Thanks for watching and all the best.